simple harmonic motion. Here you can see that the block is oscillating with the help of a spring. Such oscillatory motions are periodic. The block oscillates about natural position of the spring, moving forward and backward, having fixed time period. Frequency is defined as the number of oscillations of the block per second, and time period is the time taken to complete one oscillation. Let us understand simple harmonic motion, which is an oscillatory motion. In fact, the spring block system here undergoes simple harmonic motion. The requirement for simple harmonic motion is the acceleration should be proportional to displacement, but it should act in direction opposite to the displacement. The displacement here reflects the displacement from mean position. Let us understand this. Here the block is at the natural position of the spring, and in the next diagram, when the block moves forward, say by amount x, then this amount x is called displacement of the block. Then as the spring is elongated, it will exert force in backward direction, and therefore the acceleration is in backward direction. So the displacement and acceleration are in opposite direction. Similarly, when the block displaces inwards, that is, like in this diagram, when the spring gets compressed, that is, the displacement is negative, then the force by the spring is in forward direction, and hence acceleration is in forward direction. So again, the acceleration is in direction opposite to displacement. This is shown mathematically by the negative sign in this relation. Further, in all oscillatory motion, the acceleration should be in direction opposite to the displacement. In simple harmonic motion, the acceleration is proportional to displacement, having power 1. When this acceleration is integrated to obtain velocity, we obtain expression v equals to plus minus omega under root a square minus x square, where v stands for particle velocity, that is the block velocity. A is amplitude. Amplitude of SHM is the maximum displacement from mean position. On either side, the block moves by equal amount in SHM. That maximum displacement is called amplitude. So as we can see here, that the velocity depends on amplitude, that is, larger is the amplitude, then larger would be the velocity at some instants. Further, the term omega used here is angular frequency. Angular frequency is 2 pi into frequency. Frequency is the number of oscillations per second, and when we multiply it with 2 pi, it is called angular frequency. In SHM, the frequency remains the same and it does not depend on the amplitude. That is, if you have larger amplitude, then the particle will adjust its velocity but will keep same frequency and hence same angular frequency. The term angular frequency is determined from the characteristic of the spring, which is its spring constant and mass of the block, which we will see in next section. When the expression for velocity is further integrated, we obtain expression for displacement. The expression for displacement from mean position is given by A sin omega t plus phi. The term amplitude, it is a function of sine, so you can see that sine can take maximum value of 1, so the maximum displacement can be A. The term in place of angle is called phase. So phase varies with time. Since angle repeat itself after an interval of 2 pi, so phase will give same displacement after every repetition of 2 pi. The second term phi here is called initial phase. Initial phase represents the initial condition of the SHM. The phase is important quantity for SHM, and in next videos we'll learn about phase, angular frequency, time period, etc. Thank you.